Okay, I think most people are done, so let's just go through the answer together. Let's see. Yeah, I got 5 as well. But this was the table I ended up with, so try to see if somewhere you have something else and we can talk about this. So I once again started with just whether like this, then like this, but it shouldn't matter if you put them the other way around or not. It just transposes the table. So you start with the 1, 2, 3, and the 1, 2, 3 this way. And then for this column, for exactly, so you look at this one, this value, and this value. We take the minimum, the 0, and the letters do not match, then we do +1, right? So 0 + 1 is just a 1. And this way we fill the entire table. Anyone that with a different answer that maybe wants to ask a question or all right. I'm gonna quickly go back because I forgot to say this part. I mean, it's on the slides, but I also didn't really mention it. So the space and time complexity is m times n, where m is the number of letters you have in each word. So if you fill in a table, you're going to have m letters this way, n letters this way, right? And you're going to need to fill in each part. So it's an operation for each cell that you have. So that's time complexity is also going to be m times n. And then let's see, why is the T match not 3? This one, right? Ooh, yeah, you're right. This should be a 3. Very sharp. Let's see, does it make a difference for anything else? No, not really, right? Yeah, exactly. So the minimum value is 3, and you don't need to do the +1. So it is a 3. All right, let's see. Why is the ET equal to 3? This one, also correct. That should be a 2. But yeah, and then it also doesn't matter. Yeah, the table is a bit wrong. It's not like the last one. Yeah, and the last one we also had like yeah, it's sort of like we had what's so this part is still the same, right? We just put down the indexes more explicitly. So we still did start with the 0, 1, 2, 3, 4, etc. Well, yeah, no, I think it's fine this way. Right, but for the other one we wrote down 1, 2, like this. Why is RE5? This one? Right, so for this one we do have a 4 over here. So that's the minimum, and they don't match, so we do +1. All right, so sorry about the mistakes in this table. It was very late when I made this, but I hope like the algorithm is clear, the steps you need to take. All right. So yeah, this was the edit distance problem, and now we'll move on to greedy. I'm just going to give a short explanation of what a greedy algorithm is, and then we'll see it in action with these two. So we might have a break, not after 45 minutes, but a bit later, but it should be fine. Okay, I'm just going to move my chat box so I can also see my slides. Okay, so for a greedy algorithm, it basically makes sort of a sequence of choices to solve a problem. And at each decision point, it just makes a choice that seems the best at the moment. And the slides say if a problem is solvable by a greedy algorithm, it will also find the optimal solution. So if a greedy algorithm works for a problem, then it will be the optimal solution as well. So what greedy does versus dynamic programming is that the greedy algorithm just sort of makes a choice, the one that seems best at that moment in time, and then it will solve the remaining part of the problem, right? It also has sort of these sub-problems, but instead of just making the sub-problems smaller and smaller and smaller and solving those, it just says, okay, I have the sub-problem. I think the best choice for this would be this, and then I move on to the rest. Okay. So that's very shortly greedy, and now we'll see it in action, and maybe it also becomes a bit more clear what all these decision points are. So we have the activity selection problem, and the problem is that we are given a set of n activities. Each have a start time and a finish time, and we want to select the maximum number of activities that can be done. So we start, for example, just with the day. We say, okay, we're hanging out from 10 to 5. These are the activities that we can do, and we want to do as many activities as possible. So how are we going to select those? And the greedy algorithm says, okay, I have decision points, and at each point I'm just going to pick the activity with the minimum finish time. So you just start at the start of the day, and then you see, okay, which activity will be finished first? Okay, we're doing this one. And then we'll have the most time left for doing other activities. So let's see how this works. So we have an example over here. So let's say we have this set of activities, and these are the start times and the finish times. Okay. So we say, so these are our possible activities, and we also create just an A that's going to have the activities that we selected. So the first step we need to do is we take a look at which one of these has the earliest finish time. So we can go bowling, which ends at 12, 11:45, 4 o'clock, and we see that the first finish time is at 10. So what we do is we first go shopping. And then we remove all the activities that overlap with this part. So anything that starts between this time basically is going to overlap. So we can't go bowling because we won't be back in time to start bowling. So we can remove it from our activity list. We could go swimming if we can magically transport from shopping to swimming, which we assume we can do. We can go to the movies, we can still go diving. We can no longer follow this course. Oh, too bad, it just starts too early, right? So we remove this one as well. And then homework and lunch we can still do. So this was the first decision point, and shopping seemed like the best option. So then we move on, we check for all the activities that we still have left, what is going to be our next earliest finish time. What happens if there's two of the same exact one? If they both have the same finish time, it doesn't really matter which one you pick. That's still going to be both one activity, whether you pick the left one or the right one. So yeah, the number of activities is going to be the same no matter which one you pick, so it's all fine. So I see swimming next. Yeah, exactly. So swimming has the next earliest finish time, right? 11:45. So we're also going swimming today. Going to have a fun day, guys. And then we once again remove everything that overlaps with this. Right, so the movie start later, that's fine. We can still go diving. We can still do homework, and we can still do our lunch. So swimming doesn't really remove anything. Yes, I see a lunch, exactly. So that's the next earliest finish time. Great, I love lunch. And hey, that means I get to skip my homework. Awesome. Is there anything else we need to skip? No, right? Movies start later and we can still go diving later. All right. So then, what is our next point? Yeah, we go to the movies. Movies end earlier. So we pick this one at least. It's a long movie. I know it's a Marvel movie. And this means we can no longer go diving all. And this is our day. So we've selected 4 activities to do. So this is the greedy algorithm. At each point, it just chooses whatever seems the best. So in this case, whatever leaves us the most time for other activities. So this is a optimal solution. It could be that there is a different planning we could make in which we also have 4 activities. But the greedy algorithm just finds one of the solutions, basically. But this is an optimal solution. You're not going to be able to fit more activities into this day. All right, so a little exercise. I think this is going to be a quick exercise. So we have a new set of activities, different times. What is our new day going to be like? All right, great. All right, I think we can go through the answer together, yeah? Okay, so we have once again, we have 4 activities this day. So the furthest starting time is 11 o'clock. So first we go diving, yay. Then our next, oh, let's see which one. So we cannot go swimming anymore because it overlaps with diving. You can also not follow this course. And then we look for the next earliest finish time. So that's going to be 12:45. We're going to have lunch. So that means we can no longer go shopping. And we also cannot go to the movies anymore. And then the next time is going to be 14:30. So we can go bowling. Doesn't overlap with anything. And next we can still do our homework, which is not a fun activity, but it is an activity, I guess. So this should be the answer. Or a answer. Any more questions about this? What are other examples of greedy problems other than time slots? Well, we have another point labeling slide, which is also a greedy algorithm problem. Yeah, anything where you don't really where you're not able to sort of calculate um, the full sub problems, I guess, right? Where you don't have all the information just yet might be a greedy problem. Like, for example, do you know the card game Solitaire? Where you basically have, you sort of have all these cards, but they're face down, so you don't really know which cards they are yet. And you can make moves, doesn't really matter what moves, but it sort of slowly unravels which cards you can see. So at any point of time, you say, okay, so I don't know which consequences my action is going to have, but this action seems like a good one, and then you have more information and you can do the next decision, I guess. How are they going to ask AS on the exam? Yeah, that's a good point. I think if you understand the algorithm and the problem, then you should be able to answer any questions. But we don't really have any questions with multiple choice. We only have exams where they ask about it with like full explanation questions. So really the best we can do is just understand the algorithm and see how it works. And then you should be able to answer the questions, I think. Okay, let's see. In the instruction, decision points are just selection each new activity. Yeah, exactly. So that each new activity is sort of a decision you make. Okay, I think I had all the questions now. Let me know if I missed your question. And then we can move on to the point labeling problem. So this is also going to be solved by greedy. And the problem is suppose that we have some points, a set of points, and each point has some coordinates. Right, so in this example, we have just x and y coordinates. Could also be a 3D problem, 4D problem, whatever. And then for each point that we have, we want to make a square with a label, doesn't really matter. We want to place the square where the bottom left corner is equal to the coordinates. And then we just have square with sides 1. And we want to place as many of these squares as possible, but we don't want the squares to overlap. So for example, we count the squares for both of these points because the squares overlap. So now we need to find a way to find as many points as possible to solve this. And what greedy does, it just says, okay, we sort of sort x coordinates of all points and start with the smallest coordinate, which kind of translates to if you have a lot of points. Oh, sorry. What you do is you start with the most left one and you draw a square there. And then anything that would overlap with this is removed from your possible points that you want to use. And then you move on to the next one on the left. Right, so for example, this one, sorry, I'm drawing a bit bigger because I don't have the dots all the way down. So this one would overlap, so this is not a good point. We skip this point and we move on to the next left ones. Start with bottom left, it's an XY plane, right? Yeah, I'm kind of confused because in the slides they said just sort all X coordinates. So that would mean just starting from left and then going to the right no matter the height. But I'd also say use the XY coordinates and just start with the smallest and sort of move up diagonally to the right. Because this way, if you have, let's say we have this, and you draw it like, whoop, sorry, and that would just be 1. But if you draw it like, oh, sorry, it's a very bad drawing. Okay, let's say you start from the left, you have it like this. But you could also have this one and this one, right? So if you have it, so if you start from the left, you can only make just this one point. But if you sort of start from the lowest coordinates, this one might be the lowest if you combine the x and y. And then you might be able to do both of these. So I'd say, yeah, do start with the x and y coordinates. But the slides from the lecture set just the x coordinates. It makes more sense to use x and y, right? So I think the slides just have started with just the x coordinates for some reason. How do you decide the size of the square? Yeah, so I drew them kind of all over the place. But the definition is that they have size 1, sort of. It could be that in the problem they specify that the squares have size 2, or they say just 3 over here. Whatever that should be, that's going to be the size of your square. So that was the point labeling problem already. And you just need to sort of understand how it works. And it's more of an example of how greedy algorithm works. So yeah, try to make sure that you sort of have a first starting point with greedy algorithms, and you just kind of move on making the best decisions as you go. All right, so I suggest we have a break now. Let's do like a 10-minute break and meet back at 10:05. And I'll be here for questions, so try to, yeah, if you have questions, put them in the chat, speak up, and if not, you can have a nice break. I see we already have the questions. Okay. What questions would you expect to get on the exam related to this? Okay, so for point labeling problem, they might, I don't know, maybe give you some images where they drew the labels already and say which one of these uses the greedy point labeling algorithm. Maybe you can also expect questions on general in greedy, like how does it work? Which one of these would be a greedy algorithm? Something like that, maybe. Question, do we need to memorize the pseudocodes for every topic? No, I can't be certain, but I'd say if you understand the procedure behind it, that should be more important than knowing the pseudocode. Because if you know what procedure behind it, you can always write the pseudocode yourself, right? Okay, would you explain the added distance again quickly? Yeah, of course. Okay. So the problem is that you have two strings x and y, and you're going to need to have, need to change x into the y. And you have several operations to do so. So you can insert a character, delete a character, or replace a character. See. So in this case, we want to make the word train into fine. So we remove the T, remove the R, replace the A with an F, and we insert an E, and then we've transformed the word into fine. And what we're going to do is we write each string, we write down as a subsequence. Basically, we write it down like this. So if you have the word train, then T would be your x1, R would be x2, A would be x3, etc. And then we try to define what this last column could be. Right, so we either have the case that we do have a ladder of xi, but not from the y. We could also say we don't have a ladder from the x, but we do have a ladder from y. Or we have a ladder from x and a ladder from y, which might match or might not match. So if you do have a ladder from x but not from y, you need to delete the ladder from x to make sure it matches to y. If we do not have an x but we do have a y, we need to insert the y. If they happen to be the same letter, that's great. We don't need to do anything. And if we have two letters but they're not the same, we just replace the x with the y. So these three all take +1. Only in the case of they're the same, you don't need to do anything. And what you then do is you try to write down the cost of this, sort of as this +1 that we saw, plus the cost of the word before it. So what we see here, we have an X and an empty letter. So we say that the cost of this is going to be 1, because we need to delete this X, plus the cost of whatever was in front of these letters. And we can do this, we write it down for all the cases, and we sort of get this part. And then we need to pick the minimum value of these. Right, so we want to have the minimum value of these, so we pick it like this. And what we do then is we make this sort of table, and we start from the beginning. So we just write down a 0, and then we write down 1, 2, 3, 4, 5, 6, 7. Because in this case, you might, if you want to match the word weather to just the empty word, you need to remove all the letters, right? So the number of letters you need to remove is the number of operations you need to take. So we just fill in, this first column 0 up to 7, and then the first row from 0 up to 3. And then for each other point, what you do is you look at the cell to the left, one up and left, and cell up, and you take the minimum of this cell. So right now we'd say take the minimum of 1, 0, and 1. So that's going to be 0. And if the letters do not match, we need to do +1. If the letters do match, we do not need to do the +1. So we fill in this cell over here, and then you do this for every cell in the table. So pay attention, like if you do have that the letters match, for example, we have this T that matches over here. So we pick a minimum value, so either one of these trees, and you don't need to do the +1. So that's why this is just a 3. And this way you fill the entire table until you've reached this part. And this part tells you the least amount of operations that you need to transform X into Y, or Y into X, because it takes the same amount of operations. Does that make sense? All right, let me know if you have any more questions. Okay, we have another question. What's the running time of the greedy points labeling algorithm? Let's see. Okay, so we have endpoints. I'd say you need to sort the endpoints. Right, so you need to know which one am I going to take, which is the smallest one. And then you want to place a label for each one. So for every point that you have, you place the label, and you sort of check which ones are not, which ones overlap, right? So you check this one, for example. So everything in this double square part is going to overlap. So I'd say for every point, you check if it overlaps with several other points. I'd say you check for every point, right? If they overlap. So that's going to be n squared. And I think that's the biggest factor. I'd say n squared. But I'm not very completely sure, so I'll look it up for you as well. And I'll put it in the chat later, yeah? I mean, I can also look it up now, actually. Pause my shirt. Doo, 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 doo.
Our darkest days in the battle against COVID are
They don't say it in the slides, but I'll see if I can find it online somewhere after this course, okay? All right, so this was the break. Yeah, let's move on. I hope you're all back. So now we'll get started with the graphs. First, just quickly what graphs are, then the data structures we can use to store the graphs. Then we'll talk about the graph first search technique, and then we'll talk a little bit about whether a graph is directed and weighted. Yeah, a graph sort of looks like this, nice and tight. So you have vertices. So there's these things, and they are all connected using an edge. And each edge is an unordered pair of vertices. So if we write down the edges, we sort of write them down this. So you have an edge between A and B, but these are not directed yet. So the order doesn't really matter because there's just a graph between A and B, B and A. Yeah, so you could also have written down B.A, and it would have been the same graph, basically. Yep, so this is what a graph looks like. Not much to say about this, actually. We say that the graph is connected for every pair of vertices. So for every vertices that you have in your graph, so in this case, AB, AC, AD, AE, BC, etc. So for every pair of vertices, if there's a path between the two vertices. And a path is, did I write down what a path is? No. So a path is basically if you start from one vertex and you can move to another vertex using the edges. So this would be a path. Right, so any sequence of edges form a path. So a graph is connected if from every node you can go to each and all other nodes. So in this case it's connected. I can go from A to B, from A to E, whatever. And in this case it's not connected because there's not a path from A to D, for example. Right, and the path doesn't exist. And visually it's very easy to see. Yeah, so the fact that that these two graphs are sort of separate, right? It's not just one graph, it's sort of split into two. That means it's not connected. Okay, then we also have the sparse and dense parts. So we say that a graph is sparse if the number of edges is roughly the same as the number of vertices. So if the number of edges is kind of the same as the number of vertices. So this was sparse graph. It doesn't have too many edges. Pretty much the same number, exactly the same number in this case. And the graph is called dense if the number of edges is much higher than the number of vertices. And we're really talking about like n squared over here. So this one is dense because, well, everything is pretty much connected to everything. So we have a lot more edges than we have vertices. Question, so sparse is the same number of vertices or less? No, it could be a little bit more, as long as it's in the same sort of category, right? So it's completely fine if I have 5 vertices and 7 edges, for example, or if I have 5 vertices and 3 edges, that's also good, as long as it's kind of roughly the same. And for this one, you really do have a much higher number of edges, especially if you have large graphs, right? If you make it really connected, if you really have a lot of edges between all the vertices, yeah, it's just going to take a lot more. It's going to be a lot more dense, I guess. Yeah. So it's not really a strict anything, just more of a roughly the same. So that's graphs very quickly. And we'll see what we can do with these graphs. So we need to store a graph. So we have several data structures that we use. And the first one is an adjacency list. And this is pretty much an array, and it contains a pointer for each vertex. So over here we have 4 vertices, and we start from 1, 2, 3, and 4. And then for each point, we also make a list to all of the neighbors of the vertex. So we start from 1. 1 is directly connected to 2. 2 is a neighbor. So we put down a 2 in the list. 1 is also directly connected to this 3. So we put down a 3 as well. And 4 is also a neighbor. And so we put down a 4. So a neighbor is sort of everything that has one edge between them. Right, and then we start from edge vertex 2, and we see the neighbors are 1 and 4. So we just put down a 1 and a 4. The order also doesn't really matter. I also could have put down 4 and a 1. 3 is only a neighbor of 1, and 4 is a neighbor of 1 and 2. So we can sort of make a list like this. Then we can also make a matrix out of this. So let's use the same graphs. For some reason my mouse keeps disappearing. It's very annoying. I'm not sure. Oh, yeah. So let's say we have same graph, and we try to make a matrix. So what we do is we write down the number of vertices on each side. So we just do 1, 2, 3, 4. And for each entry, each cell over here, it is going to be 1 if there's a path between the 2 corresponding vertices. Well, sort of more of like a edge, sorry. Right, if they're neighbors. And if not, it's going to be 0. So 1 is not connected to itself, right? It have to look like this. So we put down a 0, but 1 is connected to the 2, so we put down a 1 over here. And 1 is also connected to the 3, so we put down a 1 over here as well. And 4 to the 4, etc. So we can sort of fill the matrix like this. And because this is an undirected graph, which we'll see in a bit, so if 1 is connected to 2, 2 is also going to be connected to 1. Right, so we can sort of mirror the matrix that we have in the diagonal. So if we have a 1 over here, we also have a 1 over here. If there's a 1 over here, we also have a 1 over here. So this is how you sort of make this matrix. So let's say we have n vertices and m edges in this graph. Then the time complexity of the list is going to be n plus m, because you make this well, n array parts, and then each array is pointing towards a list like this, and we'll have two parts in these lists, right? Because each edge will be in this twice. So this edge between 1 and 3 is what we have over here and here. But this is the same edge that we have over here. Sure. So technically is n, it's 2m, but the 2 falls out. So this is in time complexity of n plus m. Oh, sorry, space complexity. And then what we have over here, we need to store this n times n, entries in the matrix. This is a space complexity of n squared. Why was it 2m again? So in the adjacency list, you basically store each edge twice. So if we have an edge between 1 and 2, you'll have that it's described sort of in this part, right? This sort of says there's edge from 1 to 2. And then we also have in the vertex 2, you also go back to 1. So it sort of says you have a vertex from, so an edge from 1 to 2 and an edge from 2 to 1. Yeah, but the 2 doesn't really matter because it's just a constant. All right, so as a little exercise, try to make a adjacency list and a matrix for the following graph. And let me know once you're done. All right, so some people are done. I think some might still be busy. So I'm just going to start writing my answer as a way of going over it, but feel free to continue with your own. So for the list, I just write down each vertex first, so A, B, C, D, and E. And then I check the neighbors. So A points to B, and A is connected to C. So you just write down A, B, and C. B is connected to the A, to the C, and to the E. Oh, sorry. And that's it. C is still connected just to A and B. Oh, a question. Doesn't matter whether you put the B or C first with A. No, really doesn't matter at all. No, it should still be the same graph, right? Yeah, so D is connected to just the E, and E is connected to D and then for the matrix, do you need to put the X at the end of each list? Yeah, the X is sort of to indicate to the program that if it were to read the list, that it's the end of the list and it doesn't need to search any further. But I guess it sort of depends on how you implement this in your program. But yeah, no, it sort of means there's no pointer to the next one. And then we also have the matrix, so we do A, B, C, D, E, A, B, C, D, E, and we just check if they are neighbors. So A is not a neighbor to A, it is to B and C, and it's not to D and E. So B is not directly connected to B, it is to C and E, so C and E, and it's not connected to the D. Then C is not connected to itself, nor to D and E. And then D is connected to E, but not to itself. And E is also not connected to itself. So this would be my matrix. Oh, sorry, my pen is doing weird again. Nope, nope. I accidentally wrote on the chat box and that somehow screwed it up. Ah, yeah, should be fine now. All right, so this is my matrix and my list. Any more questions on this? See, how did the adjacency list B happen? Okay, so from B, we're connected to A. Yeah, I know what you mean. So B to A to C to E is confusing because C is not connected to E, right? So these arrows that you have here, they don't mean that A and C are connected. It just is a list of all the vertices that B is directly connected to. So B is a neighbor to A, to C, and to E. And we don't really care about any connections that we might have between the two. It's just that you need to look through the list. So the list is a sort of a linked list, right? So you say, okay, these are all the parts in here. These are the parts you need to check. So you need to check A and C and E. Does the order matter if you get a multiple choice like this? No. Order should not matter. All right. Think we're moving on then. So these was the data structures, and then we'll talk about the breadth first search. So I don't know if you had this. I think you have. So if you have a tree, right, just like a binary search tree, you can either do a breadth first search, so you sort of read this line, you read this line, you read this line, or you can have a tree and you do a depth first search, and that means you just go through the depths. So within these graphs, you also just have a breadth first search. So it's just a way of going through the graph, and you start from some node S, the starting node, and then you visit all of the nodes in order of their distance to S. right? So that's sort of if you start with S over here, and you say, okay, this one has distance 1, this is distance 1, so these are the ones we look at first, and then we look at the ones at distance 2, etc. Okay, so let's say we start with this starting node S, and we just write down everything we need to search in a queue. So this is a FIFO queue, first in, first out. Put all neighbors, sort of everything with length 1 path between it, is going to be next in the queue. So we can go to B and to C. So we put those in, and then what we do is we just look at the first node that we have. So order between B and C doesn't matter because they both have the same distance to S, or to A in this case. So we look at B, and we see it's connected to C, which was already in our list, right? This one just moved on. We have B and C. We removed B, so C is just the next in the list. But we also see that B is connected to E, so we add E in the list. So C was still there, E is added. Then we look at C. So E stays in the list. We remove the C from the queue. And we see C is not connected to anything else that we haven't seen before. So we don't need to add anything into the queue. So then the next one is E. So we look at E. And we see that it's connected from G and to D. So we just put those in the queue. We look at G, it has no other neighbors, so we don't add anything to the queue. We move on to D, which is still connected to F, and we can check F, and there is no more, no more other neighbors. So we've traversed the whole graph. So this has a runtime of n plus m. If you assume that the graph is stored in an adjacency list, because you do sort of need to check which one are the neighboring ones. So yeah. Okay, so as an exercise, try to use the breadth first search to traverse this graph. Start from this node and write down the order in which each node was visited. Just because if you traverse a graph, I don't know, you can't really prove that you traversed it, right? So I'd say write down the order and then we can compare bits. All right. So I think most people are done. It's okay if you're not, I'll go through it and then you can just compare your answer. So we start with node G. So that's the first one we write down as well. And let's keep a Q over here. So we started with G. You see that it's connected to the E. So what we do next is we remove the G from the Q and we go visit E. So put it down in the order. And then we see, okay, E is connected to both B and D. So if you put them in the queue the other way around, you will also have a different order over here. So there are multiple correct orders. As long as you use the same steps, then it should be fine. So now I have B, I'm visiting B, and I check the neighbors. So I see A, I see C, and D. Well, D is already in there, so you just have to put an A and C. And then we visited B. Then the next one in the queue is going to be the D. We check if there are any new neighbors. We still have F to go. And we can cross out D in the queue. Right, then we go back to A. So A is connected to C, which is already in there, so there are no new nodes. So we remove it from the queue and we move on to C. C also doesn't have any new neighbors, so we just remove it. And then we just need to visit F. And then we've searched through everything. So this is kind of how you do this. If you have a different order and you want me to check if that's also fine, you can just send it in the chat. How do you know which node S should be? They will give you to you a starting node. They always say like, oh, start at node G or start at node E or whatever. All right. If there are no more questions, then I think we're done with the breadth first search as well. And then we can move on to directed and weighted graphs. So directed graphs are also still graphs, but now the edges have an order, sort of. They have a direction. So this one goes from B to A. So what we had before was an unordered pair of graphs. So the order over here didn't really matter. Now it does. So we have, for example, an edge from C to A. So we start from C and we go to A. So now this is no longer the same as A to C. So that's sort of what we have in directed graphs. So what happens to our adjacency list if we have a directed graph like this? Right, so what we had first, A, B, C, D, E. First, you check all the neighbors of A. So we just say A, B, and AC. But what we have now is we also need to take the direction into consideration. So E technically doesn't go anywhere. So A just goes to X. So B now only goes to A and E. Etc. Right, so now what we had before was that every edge was stored twice, right? We technically had n plus 2m. Because we removed the direction, every edge is only going to be stored once. So now we just have the n plus m. And the adjacency matrix, I see an answer in the chat already. It's not mirrored anymore correctly. So if I were to make a matrix, sorry, it doesn't fit anymore, but you'll get the idea. Right, so still no edge from A to A, but now we also do not have an edge from A to B. So this is a 0 as well. But we do have an edge from B to A. So we write then B to A is in 1. So you sort of go from this part to this part. So indeed, it's not mirrored anymore. Okay, sorry, questions in the chat. So it still doesn't matter whether you put the A or the E first. No, order still doesn't really, that doesn't matter. As long as the direction is okay. And the N and the M, so the N is the number of vertices. And the M is the number of edges. So what we had with the unordered or the not directed graphs is that each edge was stored twice. Because if you had A, B, then you'd store it for the A and you'd store it for the B. Now it's directed, so you just store it from the B to the A and not from A to B. Right, and in the matrix, it's no longer mirrored. So yeah, that's kind of the differences for a directed graph. For the connected part, there's also a slightly different definition. So it's connected only if there's a directed path between all vertices. Oh, sorry, question in the matrix. Would there be two correct answers for the matrix depending on which side you use for which? I'd say always use from A to A. They also use that one in the slide, so I can be for sure that that's correct on the exam. I'm not sure if you change the order around, it's still correct. But I guess if you use this later on in your life and you say, you write it down somewhere and you say in your code like, hey, okay, so I go from horizontal to vertical, I switch it around. If you write it down somewhere in your, I don't know, your documentation or whatever, it's fine. But for the exam, I would definitely say just use from to like this. Okay, so connected only if there's a direct path between all pairs of vertices. So for a directed path, it's still a path, but you need to follow the directions, right? So you can go like this, that's fine, but I cannot go like this. That's not quite good. So you need to have a directed path between all pairs again. So you need to go from A to B. You need to be able to go from A to E, etc. So would this graph be connected or not? No, exactly, right? So we can give any counter example that we like, but well, A can't really go anywhere, so we cannot go from A to B, for example. So that's already a no. Right, so let's see if we can make a connected graph. Let's say we have A, B, and C. Well, if we say we go from B to A to C, and C to B, this would be connected, right? Because from B I can go to A and I can go to C. From A I can go to C, and from A I can go to B. And from B I can go to C, I can go from B, and from C I can go to A. So it's sort of a similar definition, you just need to look at the errors as well. But what we had with the first connect was that you could easily see if it's split or not, right? Like if you had a graph like this in total, you'd know it was not connected because of the two separate parts. So that no longer holds for here because this one is also not. Question connected means any point can get to any other points. Yeah, exactly. And actually, I think it should also be able to go to itself. I sort of missed that over here, but I don't think they explicitly state that the pairs have to be different as well. So over here, you can also get from A to A, B to B, and C to C. And another question, not to all though, at least one. No, you need to have a directed path between all pairs. So just one is not enough. Okay, and then we also have a new definition. It's called strongly connected. And we say that it's strongly connected if for every path of vertices A U to V. So for example, we could say A, V. There's a path from U to V and a path from V to U. Well, that's confusing me because if it's connected, there should be a path between all pairs of vertices, right? So it should already have from U to V and V to U. Wait, there was something to this. How about we just Google it, right? Which is very unprofessional, I know. But there was something to this. Let's see, directed graph connected versus what's it called? Strongly connected. Right. I think A needs to go through other ones to get to B versus just A directly to B. Okay, so it says here it's strongly connected if there's basically if there's a directed path. So let's go back to this one. So this is just a mistake in my slides, yeah. Pointer. Okay, so connected if there's a path between all pairs of vertices, and it's only strongly connected if there's a directed path, basically. So the definition of connected doesn't really change. So sorry, this is still connected actually. Well, let me also cross out the directed over here. And it's strongly connected if you can make a directed path, basically. So this is not strongly connected. So pretty much what I explained before with the connected in the directed graph, that's just strongly connected and not just connected. So connected stays the same, and it's strongly connected if you can make a directed graph to everywhere. Do you have an example of strongly? Yes, for the example that we had over here, the ABC one, this is strongly connected. So for every vertex, you can make a directed path to every other vertex or every vertex in there. What I remember from the lecture is connectivity. For every two nodes are connected, there's a directed path between them. And then from strong connectivity, for every two nodes, there's a directed graph from both V to U and U to V. Yeah, so that's also what I have over here, right? But it sort of seems like that's the same thing. So yeah, I think it is, if there's a path from B to A, then it should also be A to B, otherwise it's not strongly. Yeah, so so I think it's a slight mistake in the slides, if I'm honest. So for connected, it should really only be a path between all pairs. And then it's strongly connected if you go from U to V and if you are able to go from U to V to U. Right, because if I need a directed path between all pairs of vertices, then it already means that if I have a vertex U and V, then there is a directed path from U to V, and VU is also a pair, so you already need a directed path. So that would already be strongly connected. So question for strongly connected is not mandatory for each node to be connected to itself, right? Well, Well, it says for every pair of vertices. So I think that the pair of vertices, so like AA, would also be a valid pair. So you do need a directed graph from there. But it doesn't mean that it has to be connected directly to itself. Right, in your example that we had with A, B, C, if it's like this, then A can indirectly sort of have a path to itself. So I think that connected is not a directed graph, and then strongly connected is if it is a directed path. So if you have a directed path from each node to every node. But I will make sure. But I think it's like this actually. Yeah, so this was maybe confusing, but any questions? Oh, yeah, I'll wait. So example you gave of A to A doesn't need to be one in the matrix. C. Oh, for this one. Yeah. Well, no, because in the matrix you just look at the neighbors, right? And it's not a direct neighbor of itself. It just there's a path from A to A, but it's not a path with just one edge, let's say. So for the matrix, only look at the direct neighbors. So in this case, that would only be A, B. And then for connected, you look at the path, so you can take any sequence of edges that you like. No, AC would also be 0. So let's quickly draw it, right? So we have A, B, C. So A is only connected to B. This B only goes to C, and C only goes to A. Should sort of look like this. So the matrix is really only just one edge between them. In this case, a directed edge. And for the connected, you can look at any sequence. All right. So we also have weighted graphs, in which case each edge has a weight. So you could sort of see this like, well, if you see these vertices as a city, so you could say this is Amsterdam, this is Rotterdam, etc. And then you could say, okay, so these weights are sort of, I don't know, traveling time between the two of them, anything you like. Yeah, so in this case, each edge has a weight, and we can do some stuff with this later. Okay, so the length of the path is the sum of the weight of all edges in the path. So if I go from C to E, for example, this could be a path, right? Because the directions hold. Then the length would be 1 plus 7 equals 8. And then we also have the distance between two vertices. So we could say distance between C and E. And it's the length of the minimal length path between them. So it could be, in this case, there are not, but it could be that there are multiple paths between something. For example, it could be that this one, that there is a directed edge with weight 8, for example. And then there are multiple paths, and then the distance is sort of the shortest path between them. Right, so let's make this one a 9. So we could either take this path, and we have 1 plus 7 is going to be 8. Or we can take the direct path, but it would have a distance of 9. So this distance will be equal to 8. Do weighted edges need to have a direction? No, not necessarily. So it could be, well, for example, if we do the follow the city example, like this is Amsterdam and this is Rotterdam, it would make sense if Amsterdam and Rotterdam have the same distance to each other, right? So then it would not be a directed graph, for example. Let's see, how do you go from C to D? Well, in this graph you can't, right? Because there's no directed path to there. So there would not be at any distance between them. But usually when we look at distances, we use connected graphs or something. Yeah, so sometimes it isn't possible. So I'd say then the distance is infinity, I guess. Yeah, but usually we look at graphs where it is possible. Or we look for a certain problem in which we need to calculate the distance and it is possible to calculate it. Oh, another question. So C to A would be distance 4. Yeah, exactly. So you could take this path or this path. This one has the shortest distance or the shortest length. So this is going to be the distance 4. Exactly. And we'll use the directed and the weighted graphs in a bit with the other algorithms. But if there are no more questions, I think this is it for now. And we'll have a break and then let's do a 15-minute break. I think we have time. And let's meet back at 11:05. Right, I'll be here if you have any questions, just put them in the chat. So check this edge, this edge, this edge, this edge, and this edge. So any edge going from the graph that we've made over here. And we once again pick the shortest edge that we have. So this 2 has the lowest value. So now we put down the edge 2 and the vertex that it belongs with. And we sort of repeat this again. So now we also consider this edge, because it's connected to this one. So really just look at all the edges that we have, pick the minimum one. So we have 4, 4, 4, and then we have a 3 or a 3. So we can pick either one of those. So in example, we've chosen this tree over here. We've added it. And then in the end, you would just repeat this until you have every vertex in here. So it doesn't really matter which path you choose, but you cannot choose a path that will make a circle. Right, so let's say I have gotten to this point. This was 3 as well. And then the next shortest edge would be this one, right? So that would also be a 3. That's not possible because then we'd have a cycle in here. So we cannot do this. So you pick the shortest edge, but if it makes a circle, then you don't pick it. You just sort of skip it. So you repeat this until you have all the nodes in your graph. And then you have a minimal spanning tree, basically. Question. Let me see. Where did my mouse go? Where? So this algorithm is an example of how to get a minimal spanning tree. Yeah, so these steps that you need to follow, that's called, that's the Prim's algorithm, and it will always find a minimum spanning tree. Do you get different MSTs depending on which node you choose? Yeah, it could be, but then they do all have the same minimal weights. You can always choose a random vertex. So it could be that depending on the node you choose, you will get a different graph or different edges that you use, because you still have the same nodes, right? You just have different edges maybe. But they all should have the same total lowest weight, because otherwise it would not be the minimal spanning tree. when is the spanning tree unique? That's a good question. Mm, I don't know, if you start from a given point and all the edges are different, then you would get a different weight, basically, then you would get a unique spanning tree. I'm just not sure if there's any case in which they are all unique. But I can look it up for you. I'll write it down and then I'll look it up after the course. All right. So as an example, find the minimum spanning tree. Oh, sorry. So we can just start from any node that we like. So let's say we start from, well, let's start from D. Right, and then we need to pick the minimum edge. So we can either pick this one or this one. So let's say go to E. Then we've used this one, this part basically. Okay, and then we check the new minimum edge. So we can pick all of these edges because these are all directly connected to the part that we already have. So 2 is going to be the smallest. So we now connect E to B using this 2. Okay, then we can also create this edge. So let's see, now the 5 would be the shortest, right? But if we put the 5 over here, then we get a cycle. So we just ignore this one and we look at the next shortest one. So that will be the 7. So we can make it 7 to the A. Okay, then we have 8 or 8. So it shouldn't matter which one we choose, but if we choose this one, we get a cycle over here. So what we do is we pick this 8. I need to move my chat box a bit. Let's see, so we get 8 to C. And then we can also consider this weight. So now we add 4 to F. So this should now be a minimum spanning tree. Right, so you could also start from other nodes, and the edges might be different, but the weight should still be the same in the end. Can you also remove the D to E and use D to B instead? Yep, because they both have the same weight, right? So we could have made that choice in the beginning as well. So because they both have the same weight, these are both minimum spanning trees. They just look different. Yeah, so that's Prim's algorithm. Oh, sorry, I don't understand the step from A to D. Okay, so what we had at this point was pretty much this, right? And then we look at all the possible edges that we can take next. So we could have picked D to A, could have picked B to A, or we could have picked this one. And we just need to find the shortest one. So we could either have 8 or 7. So 7 would be the next shortest path, and we choose this one. Does that make sense? Yes, all right. Great. So then we also have to talk about Prim's running time. So let's see. This is the official algorithm, but it does the same thing that we just did. So we have the initialization of the initialization of keys of vertices. Yeah, basically what they do is they say we start with keys all infinity, and then we start with starting node has 0 pretty much. And then for each, they extract the next minimum path and then they add it to this. And then, yeah, I think it might make more sense after we've done Korsakoff's algorithm. But this is the algorithm that we do. So we need to construct, like what we did before, right? We need to find the minimum edge. So what we do, we have a binary heap that stores this, and we need to make this so that we can easily find the next edge that we need to do. So to construct this binary heap, we take n time. Then the body of the while loop executes n times. So this is pretty much for each vertex we do something. And then we extract the minimum edge. So like what we had before in the min heap, if you want to dequeue the minimum edge or whatever, a minimum key, you need to have log n time. And we do this n times, right? Because each edge that we add to our graph, we need to find the next minimum edge. So we have n edge, we have n vertices, so we do n times log n. That's what it takes to find all the minimum edges. Then we have a for loop for each vertex. Oh wait, I thought the vertices were n. Oh no, right, it does this for every edge. So edge is n. Let me write this down. And n is the number of vertices. Okay. So for each vertex, so this is going to be n times. We're going to sort of adjust this value of infinity that we had in order to find the next path that we need to choose. So this is also just a way of finding the next minimum path, sort of. So we just need to know their value first. So we can access it in one time. We need to update a key. So that's going to make, we give it a new value over here. That's sort of what we do. So if we want to update something in a min heap, you might need to change everything on every layer of the tree. So that's going to take log n time as well. Right, because this stores the edges, so that's why it's log n, and we do this for edge vertex, so it's m times log n. And then we can sort of add it all together, so we have the n log n over here, plus the m log n from over here, and we sort of assume always that the, not sure why actually, but in this case we apparently assume that the m is bigger than the n. But it also doesn't really matter, right? If you, I'd actually say keep it like this, because you might be able to express the m as a function of n. For example, like this. Okay, so this algorithm is going to make more sense in a bit, I promise. But for now, let's just do the exercise on prim trees, or finding the minimum spanning tree using this prim algorithm. So you can start from any node that you like, just pick the next minimum edge until you've created the tree, and let me know if you're done. Oh, sorry, I missed the question. What does the U and R stand for? Okay, so R is sort of the starting node that you pick, and the U, U are all the other nodes, sort of, or the neighbors. U are all the neighbors of the edges or the graph that you're considering. All right, so let's do the exercise, and I promise it's going to make more sense. I know it's a bit fake now, So once we done the Kruskal algorithm, the prim will also make more sense. All right, that's great. Let's wait a little bit longer. And then we'll see the answer. All right, yeah, let's go into it. So this is a version of the answer. So if we calculate this one, the weight should be 99, I don't know, units. So check your tree if it looks different, and if it also has this minimum total weight, then it should be a correct answer, as long as it has no cycles. All right, is there anyone with a different answer that, I don't know, wants to discuss or ask a question maybe? No, all right. Then we're moving on to the Kruskal. So Kruskal algorithm is pretty similar, but also a bit different. So given also a graph, you start with the shortest edge. And you can pick any in case of 2. So we sort of start with this edge and we include the vertices that are matching towards it. Then we choose the next shortest edge and add it as well, given that it doesn't give a cycle. Then you choose the next shortest edge, and as you can see here, it doesn't have to be connected in order to be added to it. It will eventually be connected as well. And then we choose the next shortest edge. So over here we could have also picked this one or this one. Anyone is the shortest, it would be fine. But we picked the one with 3 over here. Then the next shortest edge would be a 3. Then you'd say, okay, the next shortest edge is this tree. But this would create a cycle, so we don't pick this one. We pick one of the 4s. And we get it over here. So you just kind of also repeat this until you have a minimal spanning tree. So the difference between Kruskal and Prim is sort of, well, with Prim you start from 1 node, and you try to find the next node given all the neighbors. And for Kruskal, you just pick the shortest edges, and they don't even need to be connected. And this will also give you a minimal spanning tree. Okay, so this is kind of a yeah. Okay. this is sort of describes what we just saw, but I think the visual part is nicer. It also runs in the same running time as the print algorithm, and we'll do a little example. So we find minimum spanning tree for this one. So we start with the shortest edge, which is going to be the 2. So the B and E are connected with the 2. So we've done this one. Then the next shortest edge is going to be this 4. So we just add the, let's see, where did my mouse go? No, over here. We just add the C and over here, which are connected by 4. So then we've also done this part. Then we need to find the next shortest edge. So we can either pick this one or this one, doesn't matter. So let's say we pick this one. Sorry, we've done this one. And then the next shortest edge is going to be this 5, but this would create a circle, right? So we do not pick this one. Instead, we move on to the next. So we have a 7. And then we move on to the next. So we have 8 and 8. This one would create a cycle, so we don't pick this one. So then we have this 8 over here. And then we should have the minimum spanning tree. So this is how Kruskal's algorithm works. And when I said that you understand Prim better after Kruskal, I kind of meant Dijkstraat, but I forgot I mixed them up. But I promise you'll understand better after the Dijkstraat one. Okay, so for the Kruskal, I also have an exercise. So try to construct a minimum spanning tree using the Kruskal's algorithm. And yeah, let me know when you're done. All right, I think most people are done. So let's go through this. Yeah, so this is once again just a answer. It is the same graph as the previous exercise, and we still get 99 as a total weight. So this is the what we get for Kruskal. So you could have something different if you wait. Let me see. Are there any edges with the same? No, this should be pretty much deterministic. There are no edges with different weights, so you should not be able to have picked something else. So yeah, this should be the answer. If you want me to go through it, then yeah, let me know. So this one is unique. Yeah, if you follow the Kruskal algorithm, there should not be a different way to do this. Right, because you always start with the smallest edge and you move on to the next smallest edge, but there's not any point which you can choose different edges. All right, any more questions? No, right? So the codes might seem a bit weird for the prim and the crucicles as well, but if you just follow like this, it should be actually be pretty easy. So this was the crucicles algorithm, and we'll go into the Dijkstra in a little bit. But first I have this evaluation form for you guys. If you have the package deal, you do not need to fill this in yet. You can fill it in on Sunday. But if you just have the crash course, please fill in this evaluation now. You can just scan the QR code or go to your Athena portal. You should be able to find the evaluation there as well. It should just be 5 questions, simple questions. And let me know if you're done so we can move on after. Or let me know if you can't open it or anything. What was the running time of Cruise algorithm? The same as Prim. So that's going to be m log n. Oh, sorry. Hmm. All right. There should be some people who can fill in the evaluation form right now. I know most of you are doing the dress rehearsal. Are the artists able to open this QR code? People that are able to fill it in now, so we really need as much as possible. All right. I think we're moving on. If you haven't filled it in yet, there's also a link in your email you can use, so you can fill it in after the course as well. Yeah. So Dijkstra's algorithm. First, we need to define a problem for which this algorithm is going to find a solution. So we have the single source shortest path problem. We start with the directed and weighted graph, and we want to find the shortest path from a source vertex to each vertex u. So let's say we have a quick little graph. We say this is our source vertex. No, let's give it some edges as well. We want to be able to find the shortest path from this vertex to this vertex, as well as to this vertex and to this vertex. That's sort of what we want to do. And we have a nice little algorithm for this, and we're just going to go through it step by step. Sorry, I woke up with an itch in my throat. It's kind of annoying. Okay, so let's see. For each vertex, we start by setting the vertex weight sort of equal to infinity. So for each vertex that we have, these are the vertex names and these are the weights. We set it to infinity. Except for the starting nodes, the starting node will have a weight of 0. So we start with C in this case. Okay. And then we have this sort of empty list. So this is going to be the set of vertices for which we have computed their final shortest distance. So that's the shortest path from source vertex to that vertex. And we start a minimal priority key that stores all of this. Okay, so that doesn't really matter. What we do as well, the queue is still not empty. So all of these values are stored in the queue that we created, and we need to make this empty. So we need to go through every node, basically. We're going to extract minimum, and then for each vertex, we relax the values. So, oh, sorry, like this. And pretty much what relax does is, we'll see it in the fits, okay? So we start from this node, and then we look at all the neighboring nodes. So now we look at this node, and this node. And what we want to do is we want to see if we can decrease the value that we have in here, if we can make it smaller. And we want this value to be the path that we can take. So for now, we can go from 0 to A, sorry, from C to A with path 5. So what we do is we create a 5 is smaller than this infinity, so we replace it. Then for this one as well, we can go there from using this path. So it's a 1 instead of infinity, and this one has an 8 instead of infinity. So we just replace it. This is the relax function, basically. And so what you do is, if you start from this node, is the value that you have in here, is it smaller than pretty much going from the other source plus the weights from the other node to this weight. Okay, then what we do is we pick the next node with the minimum weight. So you go to 1, we visit this one, and then we once again look at all the neighboring nodes, and we try to relax those as well. So now from node A, we can go from B, which is 1, plus 3, which is going to be 4, and this is smaller than the 5. So we can replace this 5 with a 4 because we found a shorter path. And then this infinity one, we have also found a path from 1 to 7 and 1, 7. So that's 8, which is smaller than infinity. So we update those values as well. And then we check out the next vertex with the lowest value. So now we check for this vertex. And we try to update any neighboring values, but since there are no outgoing edges, there are no neighboring no neighboring nodes, so we don't have to do much more. Now we just move on to the next one with the lowest weight. So let's start with this one, the D, and we try to update any edges around as well. So now we have an outgoing edge to this one. So we can see if we can update this. So we had a score of 8, and now we can go from 8 plus 2 is 10. But 10 is larger than 8, so we so we just keep it at 8. And then we visit this one as well, and we visited them all. So remember our problem. We started from a source vertex, and we wanted to find the shortest path to all other vertices. So now we know that the shortest path to A is a path of length 4. This one has a path of length 1. This one has a path of length 8. And this one also has a path of length 8. So these numbers are pretty much the answer to our question. Any questions? No. All right, that's great. So you're ready to do the exercise? Okay, so the first vertex is S, which is this one. So try to find the remaining, try to find the edge distance, the shortest path to the other ones, using the Dijkstra's algorithm that we just saw. And let me know if you're done or if you need help. graph, sorry. Yeah, yeah. This should be the graph, the exercise. Question, so once we reach E, we go back to A and look for the shortest weight and then all the way back to S. Let's see. Yeah, no, you don't have to go all the way back to S. Just find the shortest weight. I'm not sure if it's A at the moment, but probably yes. All right, a few people are done. Let's do like 1 more minute. Oh, I see more people are done. Okay, let's show the answer, okay? So this was the answer. So yeah, these are the short of path lengths. And you can see this in this exercise, we will also save the path. Can I go to C to E? Let's see. Yeah, that should also give you a path of 4. Yep, that should also work. So for this one, there's also multiple options, of course. If you have at some point multiple weights, then there are also multiple answers. Is there an order, or will they just ask what the tree path will look like? I think they might just ask you for the weights, right? Because no matter the order that you have, the weights should always be the same, always the minimal weights. They might ask you for the path, but I'm not sure they will. Or they might give you an order, like if you have equal weights, pick the first number in the alphabet, something like that. Let's see, because you went SAD, not SAB. Yeah, so we didn't really have an order, so if you have a different path, that should be fine as long as you have the same weights. Vicky, what will be the path of this? If you went from SAD, or I'm sorry, I'm not sure I understand. Right. Let me know if you're still typing. We can always go back to your question. But this was my planning. It was done actually. Sorry, there's a question. Would they ask the order you went in terms of paths? Because first I right. I think yeah, no, they probably won't ask you to do this. Because I asked you to write the order down because if you do the breadth first search, there's not really a result. It's more like you're traveling through the graph. And for this one, you do really have a result because you have the weights for each node or the shortest path. So you can sort of prove that you did it and that you did it correctly. So I don't think they'll ask you the order in which terms you went. All right. So we still have like, what is it? 10 minutes left because I'm kind of done. This is my summary. So we went over the added distance problem, the activity selection problem, point labeling problem, a little bit about graphs and how they work, how to traverse them, how to find minimum spanning trees, and the single source shortest path problem, for which we use the Dijkstra algorithm. So are there any questions left we can go over now? Do you want me to go over the running time of the print algorithm maybe? Yeah. Can you go over the point labeling problem one more time? Yeah. Points, all the way up. Sorry. Okay, so the problem is basically that you have some points and points, so all these points that you have over here, they have some coordinates. So in this case, they have an x and y coordinates. And then you want to sort of place a square on top of these points, and they start like this. So the left corner is going to be the coordinates that you have. Each of these squares have a size 1, or this over here it's specified that each of them have size 1. So it could be that in the problem they give you square 2 or whatever. And the goal of this is that you want to place as many squares as possible, but the squares are not allowed to overlap. So this is incorrect. And then the greedy algorithm says that if you start, if you start from the leftmost left coordinates, and then you just place squares as you go, then you should have the most space. So I think that would be correct in like a 1D scenario where you only have the x. If you have x and y coordinates, I'd say try to find the smallest combination of x, y. Like if you draw a normal graph at the origin, and you have all these x and y's, try to find the one closest to the origin, I'd say. And then move on along try to move the furthest away from the origin as you go. And I think that way you'd be able to fit the most squares in. Right, so if you have only x coordinates, pretty much, you just say, well, I start from the most left one, so let's have to start here, and then I'll put in all my squares. And if you have x, y coordinates, try to go this way. I hope that makes sense. Are you going to give the exercise class on Sunday? Yes, I am. So I hope to see you all there. Also, if you're following the exercise class and you have a specific problem you want to know more about, just send it to me. I'm still working on all the exercises, so I can probably fit it in. I was going to look into the running time of this because I wasn't sure. But I think it is O n squared, but I'm not sure. Yeah, not 100% sure. But my logic is you for every n you try to find the you try to put the label, right? You try to put square, and then within this point you also need to check which of these points are now overlapping and need to be excluded. So I'd say for each point that you have, you do n checks of whether other points overlap, so that make it n squared. But I'll see if I can find a more official answer. All right. Any more questions we need to go over? Anything you want me to repeat? Any exercise that was unclear? I think it might be best if we go to the prim running time again. Okay, so this is the official prim algorithm. Oh, never mind. Quickly go over Crisco again. Yeah. Oh, some other quick questions. Do you know where we can do more practice problems? Well, there are very little exams like leaks about this course. The teacher keeps it all pretty private somehow. But I've tried to make some practice exercises. Those will not be exam questions, but they'll, I don't know, sort of be like this, right? Try to find the prim minimum spanning tree. So if you have any specific topic, you can just let me know in the WhatsApp group. Can we have a question about the route cutting problem on Sunday? Yes, I'll write it down. And I'll put one in. Yeah. Okay, so we wanted to go over Crisco again, right? Okay, so for Crisco algorithm, you're given some graph, any network like this. And what you do is you pick the shortest edge. So it doesn't matter if there are more, you can just pick one. Anything that has the shortest edge, you just write down the edge and the nodes connected to it. Then you pick the next shortest edge. So in this case, we have two edges of 2. And they happen to be connected, so we just write them down like this. And you keep trying to find the next shortest edge. But you have to make sure that they don't create a cycle. Right, so we have a few options of 3, so you can just pick any one. So let's write this one down. They don't need to be connected. So that's also a difference between prim and Crisco. For prim, you sort of start from the node and you build from there. And for Crisco, you just have a few separate graphs perhaps, and then you merge them together at the end. Or at least they will be merged at the end. So now we have this tree. For example, you can pick this graph next. So this connects the two separate graphs that we had over here. And then you say, okay, the next shortest graph is going to be the tree over here. But this would create a cycle, so we don't use this one. And we move on to the next shortest one, which are the 4s. So we also can't use the 4 that we have over here. That would also be a cycle. So we can just pick any of the other 4s. Oh, yeah, see you later. See you Sunday. So question for Crisco and prim, all nodes have to be included in the final solution. Yeah. Yeah, because a minimal spanning tree always has all the other nodes as well. So it's sort of like a subset of the edges that you pick. Okay, any more questions? All right, I was going over prim's running time, right? Okay, so for prim, you could also sort of do it like this. So let's say we have a few nodes and some edges between them. Okay. So you'd also say I start from infinity. And for my starting node, I start at 0. Okay, and then you need to find the next. Okay, so then we have this h. Sorry, I keep losing my pointer. It's very annoying. Okay, so we have h, which is the binary mini that stores the vertices of G. right? And then so we're going to remove elements from this H. I'm sorry, I really can't see my pointer. Oh, there it is. So it doesn't match with the gray, right? So we're going to empty this via min heap from the vertices that we have already used. So what we do is we extract the minimum element of this. Yeah, so our U over here is going to be the next minimum element. And then for each vertex V, we're going to adjust the value that we have in there. So we're going to adjust the infinity that we have in there. Each neighbor of this U. So for each neighbor, we're going to reconsider the value that we have in here. And if this, but only for the values that are still not used, pretty much. Right, so the weight that we have already set it in as infinity in the beginning, if it's smaller than if the weight between U and V, so that's the minimum node that we're looking at right now, and then the node that we're considering, if it's smaller than the key value that we have, so this is the infinity at the moment, then we're going to replace it with this weight. So we're going to, just like in the Dijkstra, you're going to sort of try to minimize the weights, and then you move on to the next weight, which is also the smallest. So for the running time, let's see, we have this entire thing. So we have the initialization of the keys. So yeah, we need a key for each vertex. So this is the infinity in the beginning, and we have n vertices, so that's going to take n time. Then we need to construct the heap, which is going to take n time. And then we have this while loop that's going to execute n times, right? Because we do this for each edge in there. Wait, sorry. We're doing this for each edge, each vertex in there, right? Sorry, yeah, this should be the vertices, I think. And M should be the edges. Okay. So we construct the H when we put all the vertices in. So that's why it takes n time. Then while it's not empty, so that's going to be n times. This is going, and then we extract elements from the min heap, which is taking always log n time because it's a binary min heap. And we do this n times, so that's going to give us n log n. And then the for loop that we have over here is going to execute for each vertex. So that's going to take m times. Then we can access each vertex in one time. But we need to update the keys, right? If we sometimes change key values. So we need to update the min heap, so that's going to take log n, which we do m times, so we have m log n. So the overall running time is going to be n log n plus m log n. And I think we sort of assume that this one is smaller. And that's why we ignore the part over here. So that's the running time of Prim. And what's the space complexity of Prim? We sort of work, let's see, within H, right? And I think you should probably store the values somewhere as well. So H is going to take all the vertices. So H has a space of n. And for each vertex, you're going to want to store, no, you don't need to store it. And you're going to need to store the graph somewhere as well, or like the minimum spanning tree basically. So you have this H plus the tree that we have. So it kind of depends on how you store the tree. Right, so if you use the adjacency list like we did before, it's going to be n plus m. If you use the matrix, it's going to be n squared, etc. So I hope this is more clear now. I know it's time, so if you want to go, you're free to leave. Let me go to my end slides. And then Alexandra, I'll go over your question in a bit, yeah? see. So yeah, I'll post the slides in the WhatsApp group. If you have any questions, please also put them in the WhatsApp group. I want to create some more practice questions, so I'll put those in the WhatsApp group as well. If you have any specific topic you want to have more about, just let me know. If you have a specific topic you want to hear about on Sunday, also just tell me. And for those of you I don't see anymore, good luck in the exam and good luck practicing. Okay, so Alexander, can you go over the traverse queuing again? I always forget to show the right order for FIFO. Yeah. Right, okay. So for breadth first search, we use a FIFO queue, which sort of stands for first in, first out, right? So for each node that we have, we're sort of going out this way and in this way. Right, so now we're going to look at E. So we remove from the queue, it's going to be out of there, and we put in G and D. So we just stuff G and D in there. And G was put in first and then D. So now we're also going to look at G first. So G doesn't really have anything, so we remove G from the queue. We just need to look at D still. So what we do is D is going out and F is going in. Yeah, see you Sunday. Goodbye. And for if you want to write down the order, pretty much every time one of these is removed this way, you just write it down. So let's see. If I start from G, I just write down G. Then I have to move to E. Right, so that's put the Q. Okay, so the Q started with G, but I removed the G and I put in an E. So for my order, I write down the G as well. Then I'll take a look at E and I see, okay, I have to add the B and the D. So I put them at the end. And the E can go out this way. So we write down the E as well. So question, do you do G is 1, and then 2 GE? Yeah, so you first look at G, and while you're looking at G, so it's sort of removed from the queue already, you notice that you next have to look at E, so you put E into the queue. So if I have a queue like this, for example, no, sorry, let's say I have A, B, C, D, not related to this graph, but I'd first look at A, and then I'd say, oh, A is also connected to, well, this F and the Z we see. Then I remove A, and I first look at the B before I move on to this F and Z that were just in there. So we just finish what we started, sort of. And let's see, and the graph first, yeah, there are several possible answers. So yeah, if I start from G and I go to E, then from E I could go to B or D. You could pick either one. So there are possible orders that you could follow. Yeah. All right. Maybe we'll see you again. Good luck in the exam. And if there are any more questions, I'll be here for a few more minutes. But I don't know, time's up, so you're free to leave. If you haven't done so, please put in the evaluation if you need to do it now. Oh, sorry. Yeah. That's great to hear. Good luck. I hope you learned something. And if you have any questions left, just put them in the WhatsApp group and we'll try to answer them. Okay, thanks guys. See you Sunday.